Welcome back, physics fans. We're going to dive into electrostatics in a moment, but to understand electrostatics, we need a new viewpoint on gravity. Here we go. So, gravity, and you don't have to take notes, this is just something to, hey, well, that's a new perspective because everything I'm teaching you here is old hat. You know it. When we were on the surface of the Earth, Mr. Curl said that there's a gravitational field strength pulling us down of 9.8. Objects accelerate downwards at 9.8 meters per second squared. We calculated that there's a force of gravity is equal to mg, and I gave you this as 9.8, and I did give you the units of kilograms meters per second. Newtons per kilogram, my bad. And G was titled the gravitational field strength. And its units are in newtons per kilogram, not what some people write down as meters per second squared, because meters per second squared is an acceleration. If I called it the gravitational acceleration, okay, meters per second squared. But it's called the field strength, a field strength, gravitational field. Okay, now there was another way we learned how to calculate gravity, and that was G, capital G, mm over r squared. Okay, that was the same gravitational force, just calculated a different way. Why did we have to introduce this? Well, because if we didn't have G, if we didn't know what the gravitational field strength was, we could still calculate the force of gravity. Because G is not always 9.8. G changes. The higher we go away from the surface of the Earth, G changes. Okay? When we had a calculation of the force of gravity, we could relate it to Newton's second law and call that the net force. So mg is equal to ma, and the masses do cancel. So the gravitational field strength does create an acceleration in an object, will have the same value, and that's why some people would write down g is equal to 9.8 meters per second squared. But it's a gravitational field. What does a gravitational field mean? Okay, well, let's take a look. We're at the Earth, and we go further out here, and we just take a look at this space that we have here, this little place that I'm going to call my special place, and there's nothing in it, right? But it does have something happening because there's a large mass here of the planet, and it's kind of causing a gravitational field trying to pull all objects to it because all objects are attracted to the Earth. So there is something happening in that space, but there's nothing in there. There is a gravitational field there. There's a gravitational field there. What does that mean? It has the potential to apply a force if I put an object there. So if I put a small mass there, it will have a small force pulling it there. How much will that force be? That force is going to equal to m, the amount of mass that I put in that gravitational field. That gravitational field exists whether there's a mass there or not. And if I put a larger mass there, I'll get a larger force there. And that's what the gent was answering to ahead before this video recording here. because it applies a force depending on how big the mass is in that field. So the gravitational field is there, and it has the potential to apply a force if you put a force there, if you put a mass there. And the larger the mass, the larger the force. But the larger the mass gives me the larger the force, but then why doesn't it accelerate more if it's a larger force? Because the mass used in Newton's second law is the same value of the mass. So if I get a much bigger mass here, that mass is going to be bigger here, so but G is still going to be equal to A because of Newton's second law. So it has the potential to apply a force. And that's a better use of the word potential because this little area, let's take another little area, there's a little area, it'll have a gravitational potential there. It'll have the potential to apply a force. If I put a mass there, boom, force exists. If I put a mass there, the force exists. But the gravitational field exists there already. There's a gravitational field strength there. How do we calculate what that gravitational field strength is there? Well, we could put a mass there, calculate its force, and then get G. So G is going to equal, measure its force, divide by the mass, and that'll be the G. So we have to put a mass there. We have to put a mass in there to get that gravitational. Isn't there another way besides putting a mass there? Sure there is. Force of gravity is this one. mg is equal to G m1 m2 over r squared. They both calculate the same value. They both calculate the same value. Two different ways of calculating it. This one needs the mass in that location. This one needs the mass in that location and the other mass. But if I cancel out those masses, we can calculate G by going G mass of the object creating that gravitational field over how far away from it. So there's a G there. What's its value? Well, this constant times the mass of this Earth divided by how far away from it. You don't need to place anything in there to create that gravitational field that's there. So a gravitational field strength is the potential to apply a force to an object. If I put a mass there, boom, force is there. That's one aspect, a new viewpoint at it. We can also bring that to potential energy as well. If I have an object up here above the Earth, we could calculate its potential energy by mgh, but that is only if g is constant throughout that, and if g is not constant throughout it, we just learned that potential energy can be calculated by negative g m over r. Of course, this is when potential energy at infinity is equal to zero. So there has to be an infinite point there. But the idea here is we have potential energy. Now, I don't like the term potential energy. We understood it as the potential to have work, but that energy is there. It's not potentially there, it's there. If I have that object there and this mass of the Earth here, it's not potentially that it has energy, it's there. And it has that much potential energy with respect to infinity. It's potential energy. Now, here's a new aspect that you haven't thought of ever. and it has to do about gravity. Kind of like the force applying to an object, and it has a gravitational field pulling into it. What happens if it has an energy field pulling into it? We have a mass of the planet, and I have this little area here. And if I put a mass m in here, then there will be a potential energy. That object will have potential energy. How much potential energy? Negative gmm over r. But I haven't put the mass there yet. So this area here has the potential to have potential energy. If I put a mass there, that object will have energy. So that location, that big word here, location, that location there has the potential to have potential energy. How much energy will it have? Well, it has G, mass of the planet, over R, negative, times the mass that I put in that location. So if I put a mass in that location, then this will be the potential energy it has. But before I put the mass in that location, this is the potential of the potential energy. Do we ever do this in physics? You'll go through all of university and never do it this way. Then why am I talking about a potential to have potential energy? Because in electrostatics, when we start bringing this gravity to electrostatics, this is very important. This is where we can learn on how to define voltage, the potential to potentially have energy there, and that is voltage. Okay, Mr. Curl keeps on alluding to that it's kind of like gravity. Why do I keep alluding to gravity? Okay, well, in gravity we have mass. In electrostatics, we have charge. Mass is given an m, charge is given a q. That's its value, that's its letter. Okay, sounds good that you could just get rid of m's and change them to q's. Masses are what causes gravity. Electrostatic forces need charges. Gravitational forces need masses. Gravitational forces need masses. Electrostatic charges need electrostatic forces need charges. But it's actually quite interesting. This gets a little bit more fun or exotic. Mass can only be positive. Have you ever heard of a negative mass before? No. But charges can be positive and it can be negative. So this gives us a very interesting aspect to electrostatics that gravity doesn't have. And you'll understand it in a second. Force of gravity had this formula. Now, G was a constant, so I'm just going to hide it so we don't confuse ourselves with it, but it's still there. Gravity is there. It's just a constant. It's a really small constant, 6.67 times 10 to the negative 10 to the negative 11. But let's just hide it so that it's a mass times a mass by how far apart they are, times its constant, gives us the force of gravity. Electrostatics is this one. There's a constant here, just like that one, but it's charge 1, charge 2, all over how far apart they are, squared. Huge analogous. It looks identical. Mass times mass divided by how far apart they are, or charge times charge divided by how far apart they are. These are two totally different realms of physics. One is gravity and mass, and the other one is charges and electrostatics. But the formulas look identical. This is why they kind of think that there might be an understanding of what a force is behind all this, and say that there's actually only one force in the whole universe. And when we're dealing with mass, it looks like this. When we're dealing with charge, it looks like this. When we're dealing with the weak nuclear force or the strong nuclear force that binds the protons together in a nucleus, maybe it's all one force, one universal force. There's a big study in physics on that. And it comes from just this observation. In fact, when they've actually looked at to see if this is a number 2 that's exactly 2, they've gone to like 12 sig figs and it's exactly 2. Why is it exactly 2? God said so, I guess. And they've done there 12 sig figs. And it's exactly 2. These are exact equations. The formula for it actually is this. Electrostatics is K Q1 Q2 over R squared. And this is our introduction to Coulomb's law, our first lesson. Thank you very much. Subscribe, like part 1 over part 2. Just click on the next video and you can enjoy it. Remember, subscribe, like, smash, turn on that bell notification.